Welcome to another answer video. My name is Dudo. Let's look at the canal from the Spark, a closer look. Question 511. What do the subscripts of a shear stress Tor Yx mean? Okay, so for this I will draw two layers of fluid, one at Y1 and one at Y2. Now, the layer of Y1 can have a shear stress on Y2, like this. Then, if this is the shear stress of Y1 on Y2, then you could denote this as Y1 on Y2. And this is exactly how the shear stress is defined. So it's not defined as the shear stress of layer Y2 on Y1. Then it also has the subscript x, which simply means that it is directed in the x direction. So this is tau yx. Question 512. What is the orientation of the shear stress at the walls? Okay, so for this I will draw quickly a version of the canal. And we have the velocity here. Now, and the shear stress at the walls, it is a friction, so it will be opposing the motion of the fluid. So it will be anti-parallel to V. Now, at the bottom, at y is minus w divided by 2, the wall has a lower y coordinate than the fluid over here. So in this case, Tor wall is exactly equal to Tor yx. So in this case, it's parallel to Tor yx. However, at the top, at y is w over 2, we have that the wall has a bigger y coordinate than the fluid below. So the shear stress of the wall on the liquid is exactly opposing the shear stress Tor yx at y is w over 2. The magnitude, however, is exactly equal, according to the third law of Newton. Now, the consequence for the later question we will come back to. And then question 513, use a force balance over a tiny fluid element to find an expression for Tor yx, assuming that a pressure drop is responsible for the flow in the canal. Okay, so let's take this tiny fluid element here and make it a little bit bigger. Then this tiny fluid element has length dx and width dy. Then the first force I recognize is the pressure acting on this surface, which I say is dy times h. And then with h, I mean a unit of depth of the canal. So then we have a tiny surface dy times h, multiplying this times p at a location x, we have the force there. Now, on a surface with exactly the same magnitude on the other side, we have p at x plus dx. Okay, so then at the bottom we have a shear stress working on the surface dx times h. This is the shear stress Tor yx at y, and as before, we have the same surface or the same magnitude surface on top. However, now the shear stress on our fluid element is going from a bigger y coordinate to our layer of a lower y coordinate. So the tau yx at y plus dy is exactly opposite. So that's why I put a minus sign here. And because it is acting on a similar surface, I put it like this, and this is equal to 0. It's all in a balance because it's steady state. Now, I can divide this whole equation by the volume of this tiny volume. So that means dividing by dy dx times h. Then we get px minus px plus dx divided by dx plus tau yx at y minus tau yx at y plus dy divided by dy is 0. And then you can recognize the definitions of the derivatives. So this is minus dp dx minus d tau yx dy is 0. And as one can see, because it is given that there is a pressure drop going from x1 to x2, minus dp dx is equal to delta p over L. And then we have a differential equation for tau yx. And you can solve this. So then we have tau yx is delta p divided by L times y. And don't forget the integration constant, C1 in this case. But now I want to go back to my previous drawing, because we see here that we have tau yx, that it has a linear profile. It's linear in y. So we have a straight line. So if I draw it in my figure on the left, then I can only draw it like this. If I want to go through those 2 points of tau yx, which I already had. So this means that it's going through 0 at y is 0. And that means that C1 has to be 0, because if I fill in 0 for y, then I get tau yx at y is 0 is C1, and it's 0. So we can skip the C1. This is our final answer. Then 514, we're going to use this relation to find the velocity profile. Well, and because it's we can assume that it's a Newtonian flow, Newtonian fluid, tau yx is also equal to minus mu dvx divided by dy. So from the last question we had dp over ly. So here we have a differential equation for the velocity vx. Okay, bringing minus mu to the other side, we have dvx dy is minus 1 over mu dp ly. Then we integrate, leaving Vx y is minus, and then we get a half from the y times dp over L, and it becomes y squared here, plus again an integration constant, C2 in this case. And then we have to use the so-called no-slip boundary condition. And this means that at y is minus w over 2, or y is w over 2, that at the wall we have no velocity. So Vx is 0 there. Okay, let's put this in this equation. The velocity at y is w over 2 is 0. We can put this in our equation. And then we can solve this for C2. So then we see that Vx is equal to 1 over 2 mu dpl u squared minus y squared. And this is our final answer for Vx. Question 515. Find an equation for the average velocity in the canal. And a recipe is given how to do this. Average Vx is I of Vx divided by I over 1. Well, I over 1. I is given as an integral from minus w over 2 to w over 2. Filling in 1 for f here, we get this. And then this is an easy integral. Limits is w over 2 minus w over 2 is 2 times w over 2 is w. It's exactly the width of the canal. Okay. Then the top is this integral. And I immediately use the linearity of the integration. Okay. Now this first one we already encountered above. This is just the width of the canal. Now the other one is, integrate this one, is 1/3 y to the power 3 limits minus. 2 to the power of 3 is 8. Minus W to the third. This is twice W to the power 3 divided by 8. So that's W to the power 3 divided by 4 times 1/3 is W to the power 3 divided by 12. So then, and then 3/12 minus 1/12 is 2/12 or 1/6. So we can write 1/12 mu delta P over L W to the power 3. Now we need to remember that Vx average was Vx over I1 and I1 was W, so our final answer here is we still have to divide by W, leaving W squared. This is our final answer. Question 513. It says that the last three questions could also be answered for a pipe to get a similar, but due to a different geometry, a different expression for the average velocity through a pipe. And as we can see, if we exchange Rw for R and put 1/8 instead of 1/12, we get the similar expression. The question here is to rewrite the relation for the tube of above to get an expression for delta P over rho in terms of Reynolds. And as is suggested by the hint, we start by multiplying the equation for VA with a half VA over rho. We get a half VA squared over rho, and it's equal to a half VA over rho times 1 mu delta P over L R squared. So then we have our delta P over rho already here. Let's put this to one side. Now recall that for a pipe we can rewrite r, the radius, as half times the diameter. So we get a half squared is 1/4. Then we can see rho times V times 1D and then over mu. So we see here Reynolds. So let's write this again. Delta P over rho is 1 over Reynolds. And below we have a half times a quarter, so that's 1/8. So dividing by this fraction is multiplying by with the reverse, so we get 8 times 8 on top is 64. Then we have left L, and still 1D is left, and we have a half times VA squared. What you should now recognize is the fanning pressure drop equation from week 2. It's the expression to remember for F. And now you can see that we have derived analytically that for laminar flow in a pipe, 4F is equal to 64 over Reynolds. I hope you've learned something from this video. If you have any questions, we can help you on the forum. Good luck with the next exercise.